Hello again. 9.3 separable differential equations. And you will see the method that we apply to solve. Sometimes we can't, but in general, to solve separable differential equations. They're not of difficult type. Okay, so let's start with an example 5 on 626. We are given xy, y prime equals x squared plus 1. This tells us exactly what we need to do. We need to separate the variables. So y variable should be on one side alone and x variable on the other. So notice that dy over dx is the same, the Leibniz notation for y prime. I'm going to replace that. So we have, first of all, we have xy dy over dx equals x squared plus 1. These pieces, this, and this should all be on one side. Y and dy should be alone on the left. So y dy is on the left-hand side. I'm going to multiply both sides by dx and divide both sides by x. So for now we have x squared plus 1 divided by x and dx. I will simplify. So y dy, x squared over x is x plus 1 over x. We separated the variables. So y is alone on one side with dy, including dy, of course, and on the other side we have x, anything that has any term that has x and dx. Now we are allowed to integrate both sides. The left-hand side will be y squared over 2. The right-hand side is x squared over 2 plus natural log x plus a constant c. We will multiply, we want to solve for y. Solve for y. We'll multiply both sides by 2. Y squared equals x squared plus 2 natural log of the absolute value of x times 2 times a constant. It's still another constant, which is considered c. It doesn't matter. Good. So in order to find y, I have to take the square root from both sides, and I get plus or minus the square root of x squared plus 2 natural log absolute value of x plus a constant c. Notice one thing here, that this is a family of functions, not a unique function, because c can be any real number. Of course, so that the square root is still, the quantity under the square root is still greater than or equal to 0, okay? So, but it is a family of functions, okay? Infinitely many c's, okay? That's why it's a family of functions. Let's take a look at another example. So we separate the variables and then we integrate it. Good. Let's look at number 9. That's my page 2. On page 626, and we have dp over dt equals t squared p minus p plus t squared minus 1. You may say, well, this looks difficult. Not if we remember how to factor. T squared p with t squared, I will factor out t squared, and I have p plus 1. And then here I will factor out negative 1, and I still have p plus 1. So dp over dt, now I factor out p plus 1, so dp over dt, p plus 1, t squared minus 1. Now, p should be alone on one side, so this factor, I will divide both sides by it, and this dt, I will multiply both sides of the equation by dt. So I have dp over p plus 1, because we are dividing both sides by p plus 1, equals t squared minus 1. We are multiplying both sides by dt. We accomplished what we wanted to accomplish. P is alone on one side, everything with p, and everything with t on the other side. At this point, we're ready to integrate. The left-hand side is natural log of the absolute value of p plus 1. The right-hand side is t to the third over 3 minus t plus a constant c. We only put one constant. Doesn't matter. I can put c here, and then I'll combine them and I get another c. Okay, so it doesn't matter, but we only use one c. Now remember how we solve this for p. The natural log has base e. We know from algebra that e to all this power has to equal the absolute value of p plus 1. E to this, minus t and plus c. At this point, I hope you remember one property of one exponential rule that says that a to m plus n is a to m times a to n. So for that reason, I will split this 2 into e to t cubed over 3 minus t times e to c. We can go back and forth. From this, I can get that by copying the base and adding the exponents, and I can also go back and split it into a product of two exponential notations, of course with the same base. The left-hand side is p plus 1 still. We're going to change this into a constant c. So then p plus 1 would be plus or minus a constant c, e to t cubed over 3 minus t. I want to make sure that this is not confusing anybody. Okay, good. So then I subtract 1 from both sides to get the final answer. So then p equals plus or minus c, e to t to the third over 3 minus t, and then minus 1. Again, this is a family of functions because of the c. Okay, moving on. Let's see. Let's look at least one more example, maybe two. Okay, number 11, same page, 626. D theta over dt equals t secant theta over theta e to t squared. Okay, so theta has to be alone on one side and dt alone on the other. So our first step would be, let's say we multiply both sides by dt first. Let's say we multiply both sides by theta and divide by secant theta. So theta d theta over secant theta equals t. I'm bringing this up to negative t squared. So t, 1 over t, e to t squared is e to negative t squared dt. I will change 1 over secant into cosine to make it as simple as possible. And this is t e to negative t squared dt. We accomplished what we needed. Theta is alone on one side, t is alone on the other, and now we are ready to integrate. This is a typical situation for integration by parts. I will change this into sine theta prime as we did in integration by parts. So this is going to be the integral from theta, sine theta prime d theta. Here I will replace u by negative t squared. Du equals negative 2t dt. I have the t, I have the dt, I don't have the negative 2. Very easy. Negative 2 over negative 2. Okay, so negative 1/2 in front, negative 2 with t and dt, so this is e to u du. Good, we apply the integration by parts here, so theta, sine theta, minus this one prime now, the integral from sine theta d theta equals negative 1/2, e to u plus a constant c, but e to u will be negative t squared plus a constant c. One more step here. So we're on page 4. So theta sine theta plus cosine theta, because cosine prime is negative sign, equals negative 1/2 e to negative t squared plus a constant c. We are looking for theta. We cannot solve this OT. We cannot solve for theta, so we leave it as is. This is the final answer. Okay, let's also look at, let's say, 13. Still on 626, and they're giving us dy over dx. So again, this is a family of functions. We'll see what happens next when we are given an initial value. So dy over dx equals x e to y, but this time we are given y of 0. When x is 0, y of 0 is 0. This is called initial value. We are no longer determining a family of functions. With the initial value, we will determine a unique function. Okay? So when we are given an initial value, we will determine one function, not a family of functions. Okay, good. So let me change the colors here. Okay. So obviously x has to be on one side. I will multiply both sides by dx. So dy equals x e to y dx. And of course I have to divide by e to y. So dy over e to positive y equals x dx. And of course, you anticipated, I'm sure, I was going to do this. X alone on one side, y alone on the other. Now we are ready to integrate. So this is negative e to negative y equals x squared over 2 plus a constant c. At this point, we stop and we introduce that initial value. So when x is 0, y is also 0. So this is going to be negative 1. So then c equals negative 1 from the given condition. So therefore, we have negative e to negative y equals x squared over 2 minus 1. I will multiply both sides by negative 1. So e to negative y equals negative x squared over 2 plus 1. In order to solve this equation for y, of course, I will apply natural log to both sides. Okay, and let's see what happens. Moving on to page 5. So this is negative y equals natural log of negative x squared over 2 plus a constant c. We only have to multiply plus 1. We just determined it. We only need to multiply by negative 1. So y equals negative natural log negative x squared over 2 plus 1. We already determined that constant a second ago. So just making sure that this does not confuse anyone. So that is 1. Okay, good. Last problem that I would like to look at is 17. Another situation with an initial value. So this is a unique function. Not a family of functions. Okay, 17, same page, 626. So we have du over dt equals 2t plus secant squared t divided by 2u. We are given an initial value that u of 0 equals negative 5. Good. So at this point, what are we going to do? I'm going to cross multiply. So du equals 2t plus secant squared t, everything in parentheses dt. Very nice. Everything with t's on one side, with u on the other, ready for integration. So 2u squared over 2, so it's simplified the 2, equals, again here, t squared plus, which function prime is secant, so it's tangent t, plus a constant c. We are told, though, that when t is 0, these two are 0, u is -5, so -5 squared will give us c equals 25. So therefore we have u squared equals t squared plus tangent t plus 25. In order to find u, we'd have to take the square root from both sides, and I have to write plus or minus t squared plus tangent t plus 25. Wait a second, because we are told that u of 0 is -5, let's make sure. 0, 0, the square root of 25 is not, it's plus or minus, but the left hand side is -5. So only, I'll write only u equals negative the square root of t squared plus tangent t plus 25, because otherwise I will not get this condition. So if this side is -5, this side has to be -5. So only the negative solution will comply with the initial condition. So this is it, unique function, not a family of functions. Thank you.